अब हम लोग एक और क्वेश्चन करेंगे शीयर फोर्स और बेंडिंग मोमेंट पे। इस क्वेश्चन के थ्रू हम लोग को आइडिया हो जाएगा कि बेसिकली हम लोगों को साइन कन्वेंशन कैसे यूज़ करना है और किस तरह से जल्दी क्वेश्चंस को सॉल्व करना है। तो थोड़ी स्पीड भी बढ़ जाएगी हमारी। तो इस क्वेश्चन को सॉल्व करते हैं, ठीक है। तो सबसे पहले ये आप देख सकते हो यहाँ पर ए से सी तक एक यूडीएल है 5 किलो न्यूटन पर मीटर का। एक लोड लग रहा है पॉइंट लोड 10 किलो न्यूटन का बी पॉइंट पे। डी पॉइंट पे एक अपवर्ड लोड लग रहा है 30 किलो न्यूटन का और सपोर्ट कंडीशंस एक हिंज्ड और एक रोलर सपोर्ट है। तो अब इस क्वेश्चन को सॉल्व करने की कोशिश करते हैं, ठीक है। अब हम लोग थोड़ा जल्दी सॉल्व करेंगे। जो जैसे हम लोग सेक्शंस काटते थे वैसा हम नहीं करेंगे, हम लोग थोड़ा और स्टेप अपना जो स्पीड है वो थोड़ी बढ़ाने की कोशिश करते हैं, ठीक है। तो अभी देखिए इसमें यहाँ पे दो सपोर्ट्स हैं। तो पहले मैं सपोर्ट रिएक्शंस निकालूंगा यूजिंग इक्विलिब्रियम इक्वेशंस। तो इक्विलिब्रियम इक्वेशंस जो मैं यूज़ करता हूँ, हम लोग तीन इक्विलिब्रियम इक्वेशंस यूज़ करते हैं। समेशन एफ एक्स इज इक्वल टू 0, समेशन एफ वाई इज इक्वल टू 0 और समेशन एम इज इक्वल टू 0। ये तीन इक्विलिब्रियम इक्वेशंस होती हैं जो हम सपोर्ट रिएक्शंस निकालने के लिए यूज़ करते हैं जनरली। तो अब आप देख रहे हो ये डिटर्मिनेट स्ट्रक्चर है। यहाँ पे तीन ही अननोन रिएक्शंस होंगी, एक यहाँ पे दो, एक वर्टिकल और यहाँ पे वी ए मैं लिख देता हूँ, यहाँ पे एच ए लिख देता हूँ और यहाँ पे वी ई या आर ई कुछ भी आप मेंशन कर सकते हो। तो एच ए मुझे दिख रहा है मेरा 0 है बिकॉज कोई हॉरिजॉन्टल फोर्स नहीं है। तो समेशन एफ एक्स इज इक्वल टू 0 टोटल स्ट्रक्चर पे हमें अप्लाई करना है। समेशन एफ एक्स इज इक्वल टू 0 का यूज़ करेंगे तो यहाँ से मुझे एच ए 0 मिल जाएगा क्योंकि कोई फोर्स हॉरिजॉन्टल डायरेक्शन में एक्ट नहीं कर रहा है। इसके बाद अगर मैं समेशन एफ वाई इज इक्वल टू 0 का यूज़ करूँ तो मुझे वी ए प्लस वी ई वर्टिकल डायरेक्शन के मैं सारे फोर्सेस को ऐड कर रहा हूँ प्लस 30, दिस इज ऑल्सो एक्टिंग इन वर्टिकल डायरेक्शन and this is equal to 10 plus this load is 5 kilonewton per meter into 2. So we will get one equation for VA plus VE is equal to 30 plus 10 20 minus 30, that will give me VA plus VE is equal to minus 10. This is one equation that we have got. Now using summation M is equal to 0. So let us take moment about A because A is also hinged and E is also hinged. So we will have to take moment about any hinged point. So we will take moment about A. So we will get, if we will use summation MA is equal to 0, then we will get we can use any sign convention for this because this is a normal equation that we have to solve. Okay. So let us take 10 into 1. That is in anti-clockwise, that is in clockwise direction, then minus, then plus, we'll take this for UDL, 5 into 2 into 1, 5 is the UDL value, 2 is the length on which, over which it is acting and 1 is the center of gravity. So 5 into 2 total load into 1, that is from the center of gravity. Then minus, this is in anti-clockwise direction, 30 into 3 and this is also minus VE into 4. This is equal to 0. So we have considered all the loads. Moment due to this HA and VA will be 0. So solving this equation, so we will get minus 70. V into 4 is equal to minus 70. So VE will be, we will be getting minus 70 by 4, that is minus 17.5 kilonewton. So you are getting this point, we will get minus 17.5 kilonewton as VE. So using VE in this equation, VA plus VE is equal to minus 10. So we will get VA minus 17.5 is equal to minus 10 and VA we will get 7.5 kilonewton. So we have got all the three values. HA is 0, VA is 7.5 kilonewton and VE is minus 17.5 kilonewton. So we have got all the reactions. Now let us solve for shear force. Now see, I am drawing just the reactions, okay. 7.5 kilonewton at point A, then the loading 10 kilonewton is this much, 5 kilonewton per meter is this much. This is point A, B, C. At D, 30 kilonewton force is acting, and at E point, this is 1 meter, 1 meter, 1 meter and 1 meter, and at E point minus 17.5, so it is in downward direction, 17.5 kilonewton. So you are getting, I have drawn all the forces including the support reactions. So let us draw shear force directly. We don't have to cut the sections because this is very easy, and we have already studied all the processes of drawing SFD. So let us start 7.5 first. So we will draw a line of 7.5. Okay, it is a sudden jump because due to point load shear force shows a sudden jump. So 7.5 kilonewton is here. Then UDL. In case of UDL, you should remember that it is a decreasing, that shear force will get a decreasing line. Okay, like we have to calculate at B. So let us calculate at B. Shear force 7.5 minus this 5 into 1. So we are getting 2.5 kilonewton at B. Okay, then it is on the left of B. On the right of B, a sudden change of 10 kilonewton you will see. Okay, so let us draw at B. It is 2.5. So we will join this. Okay, now a sudden jump of 10. See, 10 kilonewton is acting, so this will be 7.5. So this total will be 10. Okay, this total will be 10. Now let me write this a little bit below. So this whole is 10. Okay, now again with the same slope it will go down. So let me calculate shear force. I am calculating it here. At B we have calculated shear force as 7.5 minus 5 into 1. This we are getting 2.5 kilonewton. Then at C we will calculate shear force at C. So this will get 7.5 minus 5 into 2, that is the total UDL, minus 10. So we are getting it minus 12.5 kilonewton. So it will go further down. At C we will get, so this length is 12.5 in negative direction. Okay, now we will get a constant because no load is acting here in section CD. So we will get a constant value 12.5 till D. Okay, this is D point. So I am marking just here. This is B point and this is A point. So a sudden jump of 30 kilonewton will act. So 30 kilonewton, a sudden jump will show it like this. This is D point. Okay, now this was 12.5. If it will go up 30, because 30 is acting in upward direction, we will get 17.5 kilonewton, and this will be constant because no load is acting here, and finally this 17.5 will come down to point E. Right? So you must have understood the SFD. We'll mention the signs. This is positive, negative, this is also negative, and this is positive. So we have drawn SFT. So now we'll proceed to BMD. Let us see how BMD can be drawn. So this is our loading pattern. Okay. Now let us draw BMD. We might have to calculate certain values at some points. Now it is a hinge joint. We know this is a hinge joint, point A. So bending moment at this point will be 0. So we'll start with a 0. Okay. Now we can see this is a UDL. So you know that we have already discussed that if shear force shows a slopy line, then the bending moment will be 1 degree higher, that is it will be a curve. So let us draw. We don't have to calculate all the things, just we have to calculate bending moment at some points and we will draw it roughly. Okay. So let us calculate at point B. If we will calculate at point B, bending moment will be equal to, see, this is in clockwise direction. We'll cut a section at B, right? So what we'll get is, I am drawing it here to make you understand easily, 7.5. This is point B. This load is coming here, but this will not have any impact on the bending moment. This is 5 kilonewton per meter and this is 1 meter. So if we will calculate MB, so we will get MB as 7.5 into 1 minus 5 into 1 into 1 by 2. You are getting it here. It is in anti-clockwise direction. So we will get 7.5 minus 2.5, that is 5 kilonewton meter we are getting as bending moment at B. Now let us calculate at C also. At point C, what is the diagram that we will get? 7.5. At point C we are getting it here. This is 10 kilonewton at B. This is A point. This is 1 meter. This is 1 meter. This is 5 kilonewton per meter. Okay. So at point B, if we will calculate at point C, sorry, MC, if we will calculate MC, now what we will get? MC is equal to 7.5 into 1, right? 7.5 into 2, the distance has increased to 2, minus 5 into 2 into 1 minus 5, this is the UDL, into 2 into 1 and again minus 10 into 1. Okay. Why minus? Because it is in anti-clockwise direction. Now let us write the values. So we are getting it as minus 5. See, minus 5 kilonewton meter. Okay, now let us draw let us calculate at D also, so that we can easily draw the full bending moment diagram. Okay, so at point D, let us draw the figure quickly. 7.5, this is 2 meter and 10 kilonewton load is acting here. At point D, this is 1 meter, this is point D. MD we are drawing. Okay, this is 30, this will have no impact. Okay, so MD we can write is as 7.5 into 3, it is in clockwise direction, so positive, minus this is 5 into 2 into, now see, this is 5 kilonewton per meter, this 2 is the total load, and it ceases here, so the distance from here to here is 2 meter. So we will write it as 2 meter because it will have impact of 2 meter, okay, 2 meter is the CG. Then minus 10 into 2, this is 2, okay, we can write it 22.5 minus 20 minus 20. So you will get it minus 17.5 kilonewton meter. We have calculated at D, and at point E also we can calculate. See, E is hinged, so it will be 0 here, we know this. So at E we can directly write at point A and E, bending moment at A is equal to bending moment at E is equal to 0 because it is hinged. Okay? Now let us draw the bending moment diagram also. See, at point A it is 0, we are starting with 0. Then at point B we are getting 5. So let us plot. See, I have plotted suppose 5 kilonewton positive. Okay. Now at C we will plot minus 5. See, we are getting minus 5. So let us plot minus 5. Okay, it is below the line, so minus 5. Okay. Now at D let us plot minus 17.5. So it is minus 17.5. Okay, now we have plotted all the 3 points, this and this, suppose. Okay. Now see how this bending moment can be drawn. Okay. See, this is a slope, negative slope, negative slope. Okay. So negative slope means bending moment will have curvature downwards. Okay. We have already understood this. So let us draw downward curvature. See, we will draw like this. Okay. This will all be a curve. Okay. This all will be a curve. Let us draw it smoothly. Okay. This all will be a curve. Okay. Let it be like this. Okay. So why curve? Because there is a UDL acting here. Now see, this is a straight line. So it will be straight here only. So in this portion, let me clarify it a bit more. See, till this portion it will be a curve. Okay, like this. You are getting it? See, this is 5, this is a curve, and beyond this point it will be a straight line because shear force diagram is showing constant value. So it will be a straight line from here to here, okay, and then from here to here also shear force diagram you can see it is a straight line. So we will just draw a straight line and finish it off at E, that is at 0. So this is minus 5, this is plus 5, okay, this is point B, this is point C, this is point D, this is point A, and we have drawn a BMD. So you have got, see, we have taken help from SFD, we have taken help from some points, and we have directly drawn it. So you can use this practice to continuously solve these BMDs and SFDs, and you will see that you will get highly proficient in this once you will keep on practicing. See, I have easily solved this. Now as we have drawn the BMD, now from this BMD diagram we can draw the deflection curve as well. So we can see this BMD is positive up to this point and negative up beyond this. So this is called point of inflection. As we have already discussed, this point is called point of inflection. Now to calculate, now to find out where this point lies, we have to find where this bending moment is getting 0. So let us write equations once, okay? So if we'll see, we are getting that this is between B and C. This point of inflection is between B and C. So let us cut any section XX from here, okay? So let us write the bending moment equation. This is 7.5, okay? This is up to point X, and this 10 kilonewton is acting 1 meter from here. So let us calculate Mx, okay? So if we will write the equation, Mx is equal to 7.5 into X minus 5 into X by 2 minus 10 into X minus 1, okay? X is this full length minus 1, and if we will compute it to 0, then we will get one value of X. This value of X will give the point of inflection. So you must be getting this point, how we are calculating this point of inflection, okay? So we will calculate it, it will come around 1 point something, as you are getting from the diagram also. So we will get two values because it is a quadratic equation, but we will accept the positive and a value between 1 and 2, okay? Now let us draw the deflection curve also. Now for the deflection curve, we can see this bending moment is positive up to this value, and then after that is negative. So it will have a sagging effect up to this point, and then it will have a hogging deflection curve. So deflection curve can be drawn like this. This portion will be sagging and this portion will be hogging, because totally it is negative. So you are getting this point, how we have drawn the hogging and the sagging, that is the deflection curve, and how we have calculated the point of inflection. So with this example you must be clear about SFD and BMD. Now let us take few more examples and we will solve it as soon as possible, okay? So now you have got much idea about it. Now let us solve some more problems. Now let us solve another problem. See, this is a uniformly this is not a uniformly distributed load, this is a uniformly varying load, okay? So for half of the section the load is increasing, and for the rest of half of the section the load is decreasing. So you can see this problem. Now let us solve this problem. This point is A, this point is B, and this point is C, okay? Now see, the reactions at A and C will be equal because the load is symmetrical, okay? So we can directly write RA is equal to RC is equal to total load divided by 2. Now what is the total load? Total load, if we will talk about, this is a triangular loading. So half into base into height, this is the area. So this is the total load and divided by 2, okay? Now this W that you are seeing is per unit length, okay? So if we will multiply it by L, then it will become a total loading unit, okay? So we can write RA is equal to RC is equal to WL by 4. So we have got the two reactions at these 2 points, RA and RC, okay? Now let us solve for shear force, okay? Now see, in this we will cut one section because this is a different type of problem. So you will get a broader idea how we are getting the sections and how we are getting the equation for shear force, okay? Let us cut one section from here, anywhere in between XX, Okay, so I am drawing just this section. Suppose this is Wx at a distance x, this is Ra, and this is the loading that is acting. Okay. Now see, what is the value of this Wx? Now let us draw it up in a more better way. See, this is Wx, okay. Now if we will see this triangle, suppose AOB, and this point suppose is M and this is M dash. So if we will see triangle AM dash and triangle AOB, what we will see is these are similar triangles, these are similar triangles, okay. Now with the property of similar triangles, we can write this distance is AB upon AM, this is equal to AB upon AM, this is equal to OB upon MM dash. You can easily write this. So AB is L by 2, AM, now let us write it below, AM is X, this is equal to OB is W and MM dash is WX. So from here we can write WX as W into X into 2 divided by L. Now see, we have calculated Wx, so this value is Wx. Now as we are solving for shear force, so shear force we solve it like this. We assume this direction. I have already told you, because left hand going up means positive. To balance this will act downwards. So this will be the direction of positive shear force. So to balance this Vx, we can write Ra minus this total load, because this is acting downward. So this is half Wx into x. The area of this will give you the total load. Now let us solve for this. This will give you Ra minus Wx value we know 2 into W into x upon L, and this will be one more x. So Ra we have already calculated, WL by 4 minus this 2 will get cancelled, Wx square upon L. So we have got this Vx equation. Now the point that we have to notice is that this is a quadratic equation with minus as coefficient, minus something as coefficient. So it will be a parabola with curvature downwards. So this we have cut section from here. So let us take it as section AB. This is in section AB, right? Now let us take another section here. So I am writing it as section BC, okay. Now let us take another section BC. Now you will get one idea from here. Now suppose this is the section that we have cut, okay. Now suppose this is the section x dash that we have cut, okay. Now from here you will get one idea. See, this is Ra, this is W, and this is Wx, suppose, right, and Vx will be acting like this. This is the positive direction. Now let us draw another part. This is RB, this is Wx, and this is the other part, this is the loading, okay. Now see, I have drawn another part. I have cut into two sections. This is the first part and this is the second part. We generally take this part, but in this problem the distribution of load is not uniform. See, here it is uniform. So we can solve this problem by using the equation for this section. Now see how we are taking the section. See, this is the positive Vx in upward direction for this section. So for this we will write Vx is equal to, this is acting downward, so this will balance this. So first we will write this downward load as positive because the section has changed. We are not taking the left hand section, we are taking the right hand section. So half into Wx, now this, now see, if we will take this as x, there will not be any problem because x is varying in this from L by 2 to 0, right, and in this also we can write x as varying from L by 2 to 0. You can take this also as x, no problem at all, but just to solve this, just to make it easier, we are taking this as x, no at all, there will not be any problem. So let us take half into Wx into x, this is the total loading, half base into height, that is the area of the triangle, minus Rb. Now again let us write the full equation, half into 2 into Wx divided by L, Wx we have used from here, this will be the same, so we don't have to calculate and one more time, okay. Now this minus WL by 4. Now see, we have got another equation with coefficient as positive. This is the same Vx, this Vx is same as this Vx only, okay. So we have got the same equation, right. Now see, this is there, here it is, here the coefficient is positive and here the coefficient is negative. Now let us calculate at B, from any equation you can calculate at B, shear force. So x will be equal to, here if we are calculating, x is equal to L by 2, okay. Here also x will be L by 2 because we are taking it from here, this is the reference point. So keeping x is equal to L by 2, shear force at point B, here also if you will put L by 2, this will come out to be L by 4 and this will become 0, this will come 0, okay. So shear force at B is coming 0. So now let us draw the shear force diagram. See, this is the loading, this is Ra, that is WL by 4, this is Rb, that is WL by 4, you have already calculated all these things. See, now let us draw the SFT. Now see, a sudden increase of WL by 4 can be seen here because point load is acting, it is a kind of a point load. Now see, this is the equation with negative coefficient, okay, for the section AB. So for the section AB, we have negative coefficient of x square. So parabolic curve can be drawn with curvature downward and at B it is 0. So we can draw it like this as positive, right? This is point A, this is point B. Now see, for this section, for the rest of the section, that is BC, we are getting equation this with positive coefficient. This is a positive coefficient. So if it is positive, the curvature will be upward, but the value is negative because the loads are continuously increasing. See, here it is, this load has balanced this load, but here we have a decreasing downward load. So downward load as it is increasing, it will give shear force negative. So we are getting idea from here. So let us draw a negative shear force diagram with curvature upward, and suddenly there will be upward force and it will come out to be 0 at point C. So see, I have drawn, this will be symmetrical, okay, this will be symmetrical like this, yeah. So this we have drawn SFD. Now we have drawn SFD. Now you can see how we can correlate it with the loading pattern. Now see, if you have any doubt regarding your pattern of drawing SFD, so you can correlate it with the loading pattern. This will give you confidence and will give you the surety also that you have drawn it correctly. Now see, this shear force diagram, this is a loading curve with negative curvature, right? Now sorry, this is a SFD. Now see the loading curve, this is increasing in the section AB. So W into X, it is increasing with X. See this 2 into Wx by L. You can see it here. The load is increasing in the section AB. Okay. So if it is increasing, we know that this differentiation of shear force diagram with respect to X is minus of loading curve. We have already discussed this. Okay. So see, loading curve is increasing with respect to X, so minus Wx. Okay. And if we will differentiate it, it will give negative coefficient of x square. As we are getting the negative coefficient, so it is with curvature downwards. Now see, in the second half, you know that load is decreasing. The load is decreasing, so it is minus Wx. In actuality, if we will consider from this side, this is increasing, but from the convention of left side, it is decreasing. So since it is decreasing, minus minus will become plus, and this will give you a positive coefficient on integrating. So we are getting an upward curve. So you can be sure from here that how loading curve is related to shear force. So I think this SFD is clear. Now let us move on to BMD part. See, it is also very easy. For BMD, let us take first section in AB. Okay. So this is the loading, and this is Wx, this is X, this is RA, and this is Mx. Now for this section, first section AB, now let us write the equation Mx. This will be equal to, this is clockwise moment, so we will take it as positive RA into X. This is clear. Minus, now this loading is in downward direction. Now let us see how we are calculating this. This is the total load. Now for the centroid, you know that this lies at 1/3 from here and 2/3 from here. So centroid will lie somewhere, suppose here, this is the centroid. See, so this will be x/3 and this will be 2x/3. You are getting? So this will be x/3 and this will be 2x/3. So we are calculating it from here, so we will write into x/3. So this is the total load into distance from the centroid. So this will become moment. So moment will be RA into X minus this equation. So we can write RA is WL/4 into X minus half into Wx, we have already calculated as 2Wx/L into X/3. So we have got it here, W into X cube upon 3L. See, we have got the equation of Mx. We have got a cubic equation with negative coefficient. Now see, this will help us out. How this will help us out? Let us. Now if we will calculate moment at B, what will be this? Lx will be equal to L/2. This is very clear. Okay. For section AB, X is between L/2 to 0. Okay. Now moment at B is equal to into L/2 minus W upon 3L into L/2 ka whole cube, right? Now if you will solve this MB, this will come out to be WL square by 12. Okay, if you will solve this, it will come out to be WL square by 12. So now let us draw the BMD. This is W. Now see, at point A it is hinged, so we will start from a 0, right? And see, the coefficient is negative, but at x equal to 0, right? X equal to 0, the value is positive, and as it is increasing, it will be a positive value, right? And we will get a maxima or minima at point B. Because shear force is getting 0, is changing sign at point B. So we will get a maxima or a minima at point B. So from here, if we will draw like this. So this, we have drawn half of the section WL square by 12. This is point A, this is point B. Now see, this is a cubic parabola. Cubic parabola. You are getting it from this equation. We have got this x cube as cubic parabola with negative coefficient, so curvature is downward. Now for rest of half of the section, how we have to draw? Now let us see from here. See, the value of shear force gives us the bending moment. You know that dm by dx is equal to shear force. So value of shear force gives you the slope of the bending moment diagram. So see, the values are continuously decreasing up to point B. So the slope has to be continuously decreasing. You are getting it from here? If the value of shear force is decreasing, the slope is also decreasing. So now let us come to here. Now let us come to here. The slope is, the slope is here like this, here like this, here like this. The slope is continuously decreasing. So it is clear from the shear force diagram. So the shear force diagram is here, I am drawing it here also, like this, right? So the value is decreasing, the slope is also decreasing. Now see, the value is increasing in the negative direction. The value is decreasing in the negative direction. So the slope will increase in the negative direction. Now see, the slope, how it is increasing in the negative direction? See, it is, the slope is in negative direction, the slope is in negative direction, the slope is in negative and it is increasing. See, we have proved how this is related to this. So you can draw this as positive. See, and it has come to 0 at point C, right? This is point A, B, C, and it has come to 0 at point C. The slopes in this portion, the slopes are decreasing, positive slopes are decreasing. Getting my point? Positive slopes are decreasing because shear force value is decreasing, and this is negative slopes are increasing. So I hope you have got the relation between shear force and bending moment diagram. So we have drawn the BMD using the SFD diagram. So you can correlate all the curves, loading curve, the shear force curve and the bending moment curve. Using this curve you can easily draw and verify your answer. Okay, I hope you are getting all these points. Now if we are to draw the deflection curve, then obviously this is positive and this hole will be a sagging, this hole will be sagging. So if we will draw deflection curve, see, this is a beam and this I have drawn a sagging beam. See, sagging beam we have drawn because bending moment is positive, so this beam will be a sagging beam and this we have drawn the deflection curve. So I hope this example is clear to you, and now we will move on to the detailed structural analysis part slowly. So this will give you a brief idea how we are correlating with BMD, SFD and deflection curve and the loading curve.